So many noises. Hello, everyone. Welcome to the Saturday afternoon track here at Hall C. My name is Maya, and I'm the person you probably want to come and hassle if you couldn't decide which talk to go to. If it makes you feel any better, as the program chair, I inconvenienced myself as much as anyone. I haven't been managing to catch almost any of the talks I actually want to see. Anyway, I'm here to actually introduce Dave. Hello, Dave. This is Dave Colls. Dave and I worked together at ThoughtWorks for a while, and he's the director of the data and AI practice at ThoughtWorks. Actually, I just remember Dave as being the person who created the most high-value content on the internet at work. He's full of whimsical technical data about which he is about to tell you all.
Thanks, Maya. And thanks for joining me, everyone. Lovely to see you here today, and I'll do my best to keep us all awake in this slot after lunch. And thank you, Maya, for that as well. So today's about maths whimsy with Python. But before I start, I'd like to acknowledge that we're meeting on the traditional country of the Kaurna people of the Adelaide Plains, and I pay my respect to elders past and present. I recognise and respect their cultural heritage, beliefs and relationship with the land. So today is about me sharing my experience with Whimsy, with maths, with Python libraries, how those things come together in a sprint or a short development cycle to generate outputs, learning and applications beyond that. Today's quite indulgent, it's quite personal, but I hope it's fun for us all as well. And I hope you'll take away from this maybe a bit of inspiration, some guidance around a process that's worked for me and might work for others, and resources with Python for your own journey. When I talk about whimsy, I'm not talking about being capricious or changeable. I'm talking about things that are light or fanciful, things that are quaint or unusual, that have some interest in their own right, but then it's a bonus if we are able to leverage them beyond that. And a little about me, as Maya said, I'm a director in the data and AI practice at ThoughtWorks Australia and New Zealand. ThoughtWorks is a custom software technology consultancy. In my role, I help our team help our clients solve their problems with data, maths and AI. And it might be worth talking a little bit about the path to this point. So why am I talking about maths whimsy in Python today? I think I can trace it back to high school in the 90s, where I probably started with maths whimsy in BASIC in those days. I enjoyed doing things like double pendulum simulations and drawing Sierpinski triangles. And that took me into engineering and computer science in my undergraduate, which involved a lot more engineering maths, using in those days C++ and Java, and an early career into games, engines, CAD/CAM and simulation. Then my career took me to a place that was a bit maths light after being very maths heavy for those years. And when I joined ThoughtWorks 13 years ago, I actually joined as a project manager, and I spent most of my time working on delivery improvement and organisational change. Agile transformation was a big thing that a lot of organisations were doing back then. After some time, I moved into the data and AI practice role, and in those early days, I was helping others deliver on data and ML for our clients, and typically making slideware. Thank you for the introduction, Maya, because my slideware did become a bit of a meme at the time. This from one of the team, lamenting me going on long service leave and what would happen to the quality of our slideware over that period. So how did I go from that point of, what changed in that I was making slideware day in, day out, to actually doing some work in Python and some whimsical work in Python as well? Well, I found myself on a solo advisory engagement, so I was the only thought worker on that engagement with a client that very quickly became maths heavy. And this was the kind of thing where qualitative explanations and what I could deliver in terms of ideas communicated through documentation wasn't enough. I actually needed to be able to prototype and express my thinking as code instead. So at that point, picked up a Jupyter notebook with some scikit-learn to demonstrate to this particular client what it would look like to extend their current process into the world of machine learning, how they needed to think about measuring success and the types of processes they need to put in place to manage the data. That was around about the time, actually, I think, of the last in-person Python conference. And soon after that, we moved into COVID lockdown. And COVID lockdown presented me with a lot of spare time to pursue this newfound interest in Python. So let's look at where Whimsy struck in COVID lockdown. The first instance, obviously I saw a lot of my children in those days with remote schooling. And one day, one of them said, "Dad, for school, I made a square planet." And you can see here, it's a pretty cool square planet. It's even got a little compass rose or /GPS device on top to tell you how to navigate from one face of this square or cubic planet to another. But it posed a question in its very form. It posed a question of what happens at the edges. When you come to the edge of one of the faces, it's standing on a flat plane and you're looking down over a sheer cliff, and with the danger of falling down that cliff and off the edge of the planet entirely? Or is it something a bit different? Is it more like maybe reaching the crest of an A-frame roof? And so we talked about this for a little while. We talked about considerations of symmetry that might lead you to choose one over the other, but ultimately I thought that was too simple a resolution of the question, and it needed some maths. And so we could start with, I decided to model it as a grid, and in this grid that represents space, some of the cells have mass if the planet occupies those cells. Then for each of the grid cells, if we can calculate the resultant force of gravity, then we can build up a picture of what gravity looks like in the region of the planet, and we should be able to answer the question of what happens at the corners. Thanks to Newton, we've got the maths for over 300 years. We've known how gravitational attraction works, and if we look at that over the grid, then we've kind of got a double loop for each grid cell, and we sum up the contribution of all of the masses to the gravitational field at that point. And then the Python to add to the maths. So given the discrete nature of how I'd set up the problem, it seemed to lend itself well to NumPy, which is a library that suits fast and scalable numerical processing, especially arrays of data. And because I wanted to answer the question of what does it look like, matplotlib is a really useful library for visualization as code, everything from simple charts up to complex 3D animations. So with those ingredients in place, we could start working through the process. And the process was to start as simple as possible and then take small steps in either problem complexity or solution complexity. So I knew a little bit about for loops with my programming background, and that's where I started, looping over each location and the contribution of every mass to that location. And I could validate that I could get something that, far from a square planet, at least looked like the gravitational field you'd expect to see around a regular spherical planet. And so I could confirm that I was able to reproduce the real-world phenomena I was expecting. But I did want to move beyond for loops. They were very slow. And I did want to start learning NumPy. So the next step was to try and reproduce that first solution, increase the solution complexity in NumPy instead. And the first step I took in NumPy was to use mesh grid, which some of you may be familiar with as a technique for discretizing a plane or a region of space and being able to do a calculation at each point. Doing that, I was able to reproduce the for loop and actually reduce the time by a factor of about 30. So I was quite pleased how much more efficient that was. The next step in that process, though, I was limited to square planets and square grids. I realized actually there was a slightly more sophisticated mesh grid implementation where we could mesh indexes on both the locations in space and the locations of the planet. And so that was another step in solution complexity, but I was still working on the simple problem. However, that step allowed me to tackle a harder problem, which was not just a square planet, but any weird-shaped planet in 2D cross-section. Let's see what the gravitational field looks like around that and continue to extend the solution further. And so if I visualize it, it looks like this. We've got the square planet as the starting point and the most simple solution, the for loops. then getting slightly more complicated with the NumPy version 1 and NumPy version 2. When we get to version 2, then we can start moving in the problem complexity space and look at extending the 2D solution into 3D and actually get the picture of a cubic planet, but also choose any sort of arbitrary shape. And in this case, I chose to just take an image and threshold it, and anything inside above the threshold would be mass of the planet. And then we would look at the boundary of that and figure out how gravity varied around the boundary. So to get back to the original question of what does a gravity field look like around a square planet? Well, this is the rendering with matplotlib of that NumPy calculation. And we can see that at the corners, the gravity vector indeed points into the corners in a symmetrical way rather than suggesting that there's a cliff at any of the corners. And as we get further away from the planet, it looks actually more like the typical gravity field that we'd find around a spherical planet. So that's also a good sign. So we can answer the Whimsy, and we can answer the question, what happens at the edges? It is actually like you're at the top of a roof. But if you consider how the gravity varies along the edge, it's pretty weird and pretty cool. If you're sitting at that point on the edge, you'd be looking down what appeared to be a flat 45-degree slope that you could slide off the end of and into space when you reach the far end of that face. If you did start sliding, however, by the time you reach the middle of the face, you wouldn't be accelerating anymore. You'd feel like you're on flat ground. And as you continue to travel along that face, you'd actually slow down before coming to a stop at the far end of that face and then oscillating backwards and forwards. This sounds like a pretty cool fairground ride to me. And so then we can, so with that question answered, of course, we can go a bit more complicated in the problem space and take any image, as I said. So the rubber duck here, using Pillow to do the image processing and give us a threshold. We can then perform the same calculations, find a path around the boundary of the object, which it might appear to somebody walking on the surface. They could see how the gravity varies in strength and direction. So that was a bit of Whimsy, a bit of maths, and a bit of Python. And what outcomes did I get from that? Well, I bored my kids with all the minutiae of this solution, which is a pretty common scenario in the Colls household, I must admit. But through the process, I learned a lot about NumPy operations, especially how to be clever with indexing into arrays, which I've been able to use over and over again, and kind of establish that this pattern for learning works. And as I said, I really want to visit a square planet, slide down and back up the sides. So I hope I'll be able to do that one day. But in COVID lockdown, I was stuck pretty close to home. In Victoria, we had the 5-kilometre limit and even the 60-minute limit per day. Within those limits, I was trying to find some kind of exercise to do. And I hit upon the idea of practicing wheelies on my bike in the back streets of the neighbourhood, but also the maths question of what if I measured how I was doing wheelies with the accelerometers of my phone artfully attached with gaffer tape there to the top tube of my bike. And so this was another bit of Whimsy to pursue. And another project that I could pursue in small chunks as well, slightly bigger than the square planet, but small chunks nonetheless. The first one was to build a data collection pipeline. And so each time I went out with my phone, I could download the results from the SensorLog app that I was using into something of a training diary or a Strava for wheelies, as I called it. This made use of pandas, SciPy, and a run length encoding library called Python RLE so sampling the pitch. Basically, what we're looking at here is sampling the pitch of the phone at 1/10 of a second intervals, and then from that time series data, extracting useful features such as the length of a wheelie for further analysis. And then the second, so then having that data, those richer features, I could move on to, can I build myself a wheelie coach with machine learning to help me improve my performance still further? And so the first iteration of this wheelie coach was taking the half a second where the front wheel of the bike is going up, and based on the time series trace of that, can we predict how long the wheelie is going to last? And so I was able to predict that better than random guessing with an ML model, so that was an improvement. The next step beyond that was then to say, okay, we've got the front wheel up and we're balancing. how might we predict how the wheelie is going to go from any point in the balance phase? So am I likely to keep going, or am I likely to actually lose my balance and put the wheel down again? So this was a slightly more complicated ML approach, which is a series-to-series prediction. But as you can see, I'm gradually able to layer on more and more by biting off small chunks at each time. And what I found actually, so some of those things I'd planned ahead of time, but then other things emerge as you're going. And so one of those was actually realizing that when I had enough wheelie data, I could build my own generative AI, and I could actually create more wheelie data based only on the duration, and create some synthetic data. So this is using an autoencoder, which takes 10 seconds of time series data, boils it down into just 3 data points. And from what I could tell, the model was recognizing that wheelies were either short or long, they had a gradual or a sharp landing, or they were low and smooth or high and wiggly. And then we can generate new traces on demand. If I'd built it today, I might have called it wheelie GPA. So those were some examples of just pure whimsy for interest's sake. I got some learning that I was maybe able to apply indirectly, but nothing that I was able to apply directly. Unfortunately, we don't have too many clients who are working on their wheelies at ThoughtWorks. But there are some other questions that came up that could find direct application in client work. And so one of those was the question of how to communicate the performance of machine learning systems to clients. A typical way to do this is with a confusion matrix. And so confusion matrices are great because they show us when we're getting the answer right with a classifier, but most importantly, they also show us what types of mistakes we're making, because often in classification, mistakes have asymmetric costs. In some cases, false positives are more costly. In some other cases, false negatives are more costly. But it's actually quite hard for non-experts to access a confusion matrix and to figure out what it's trying to tell them. In other areas, we've found that Sankey diagrams, which show flows or the flow of resources between states or parts of a system, are actually really easy and intuitive for clients to understand. Interestingly, the underlying data for both confusion matrices and Sankey diagrams is in the same form as a matrix. So I wondered, what would it look like to try and draw a confusion matrix as a Sankey diagram? And the answer is, it actually works. And it helped us have some richer client conversations, where in this case, we're comparing 2 different versions of a classifier, and we're comparing them to an existing process. The existing process is at both ends, so we can see manually which decisions have been given a true or a false label. And then on the left in the middle, we can see method 1, which has better accuracy, so it gets fewer things wrong overall. And then we have method 2, which has worse accuracy, but actually has no false positives in this case. And if false positives are particularly costly, then maybe we'd go with method 2 instead. By having them all on the same chart instead of separate confusion matrices, we can actually also then compare method 1 and method 2 in the middle and say what's happening where they disagree on a prediction. What are the factors that drive one model to make a decision one way or the other model to make a decision the other way? And so this was something that was a bit easier, a bit more accessible for clients that weren't expert in evaluating machine learning systems to talk about how well different machine learning approaches might work in their case. And it's also good for wheelies, as it turns out. So looking at that second stage of the coach of predicting what's going to happen in the balance phase, instead of this being a binary confusion matrix, we see it's a multi-class classification from continuing to balance or to put the wheel down on the ground. And we can also show that as a confusion matrix instead. And I think what's nice, as a Sankey diagram instead, I think what's nice here is that you visually get a sense of the size of the different classes, which can be harder to do from what's typically the heat map colouring in a confusion matrix. So it was good to see how things are starting to come together a little bit. Techniques driven by one piece of whimsy start to be applicable somewhere else. And so diving a bit deeper into the different outcomes, which I might describe as outputs, learnings, and applications from each of these mini projects. In terms of outputs, I would typically get Python notebooks and modules, and then also typically write those up into blogs or talks like I'm doing today, quite meta. But beyond the artifacts as outputs, the learning of my own and that I could share with others, and then applications in my day job too. supporting, we might do POCs or content creation for developing points of views for marketing. So there's the potential to apply these projects in that space. Setting up engagements for success, being able to anticipate problems that might come up and plan those in the early days of engagements, and also during engagements be able to support better outcomes. So lots of different applications. And having dived into a few specific examples, we can look at the overall learning pattern now as well, just to reinforce what I was talking about. And so it's pretty simple. I see something interesting, ask if there's some maths involved and what type of maths that might be, and then also ask if there's any prior art out there. And so when it comes to confusion matrices or Sankey diagrams, those things have been done before, but not necessarily in the form that I was looking for in this case. And then when I guess I've sort of evaluated that there's some value in doing something in this space, the next question is, can I break it down small enough or frame it in a way that it fits within a sprint? And I'm talking about like a typical fortnight period. But as I said, I have a day job, and so it's typically not it's not an 80-hour sprint. It's probably more like a 20-hour sprint spread over the course of 2 weeks. And so this requires the opportunity to present itself. At times in my career, I've had a lot of spare time to work on these things. At other times, I haven't. COVID obviously provided a lot of spare time to work on these things. Since then, I've had to be a little bit more opportunistic. But I think it's important to note that you can have a backlog of ideas and then wait until you have the time to pursue them. If I then recognise that I've got the time to pursue something, I can kick off a sprint, solve the problems, code them up in small steps, as I've said, write it up as well, and then look to see if there are any interesting extensions, which might lead me back to the start, and hopefully over time we'll find some applications. And it's been my experience that I have found applications over time, although that is disconnected. It's not tightly coupled to the process of on one particular project. And so this process is, because it's iterative and maybe multi-scale as well, I have some projects in their own repos, but I have this specific maths Whimsy repo, and that's why how I came to think about talking about it here. And so the maths Whimsy repo is really to lower any barriers to getting anything started and written. In maths Whimsy, I might just write a notebook, which is a handful of lines of code to do something like eliminate a node from a graph. These are things that might lead into bigger projects, or they might actually have come from the bigger projects as a sub-problem to be solved, but one that's reusable and repeatable. So I think it lives better in maths Whimsy. So you can see some examples there from what I've showed you that sit sort of on the bigger project repo side or on the maths Whimsy repo side. And one last set of examples of how things might move from one to the other. So I've just discovered another area that I tend to explore is puzzles and automating or augmenting human solutions to puzzles. This actually started back in my maths Whimsy with basic days. There's a cube puzzle called Instant Insanity, and rather than go insane, I decided to write a basic solver to solve it for me. But in recent times, I was interested in Semantle. That's another game that can drive you insane trying to solve it. And thinking about the embedding space, the 300-dimensional embedding space, how to actually navigate that in an automated way to find a solution. And so that was something that started as just a bit of maths Whimsy. And as I thought about different ways of solving it and the fact that I could actually plug in the solver into a game with friends and play it live, that then iterated and became its own project. The one on the bottom, Asteroid Escape, it's a game we have at home. 109 steps to solve the hardest one. I thought that was much better automated than solved manually. But looking at the catalogue of solutions they had, I thought, wouldn't it be interesting to generate more puzzles with interesting solutions? So that might be part 2 of that particular project. And so, looking at individual examples and how they connect together, I'd now like to take a look at the bigger picture, the cascade, as I've hinted about how different projects come together. And As I said, sometimes talking about things qualitatively helps, and I started thinking about this qualitatively, but then I realised I could do it quantitatively as well. And what's the maths in this case? A knowledge graph. So I thought, let's actually take a knowledge graph to all of these projects that I've played with over the years. And this is what it looks like for the square planet example from earlier. So I have an idea and some maths, square planet idea, the Newton gravity. There's a couple of Python libraries there, matplotlib and numpy, as I described. They come together into a sprint, which delivers a notebook and also delivers some learning, numpy development and matplotlib development. So if I'd only done one project, this would be the extent of the knowledge graph. But then, in the case of the square planet, I extended it into a weird planet, and also then did some rendering of Lagrange points around a planet-moon system out of interest. Then it starts to build some more connections. So we start to see some more inspiration, and we start to see cycles of NumPy learning, for instance, NumPy development learning back to use of the NumPy library. And then as we start to bring in more examples, at first the graph might have separated groups of components, but we can see that we're starting to add more nodes and more edges. As we gradually add more projects, then it becomes richer, and I've actually gone through the whole contents of the Maths Whimsy repo, but not all of those other projects that I showed you on the right-hand side of the diagram. So this is what it looks like with everything in the Maths Whimsy repo in there. And so what comes out, and maybe it's a little bit of an artifact of how I modelled it, but definitely that the libraries and the sprints are central concepts in the graph. So that's where things come together, where ideas come together and get turned into outputs and applications. And the learning that I modelled, it participates in cycles. So I find the learning comes out of the process, but also goes back into the process as an input. The Whimsy and the maths are the sources, and the outputs and applications are the sinks in this graph. And there's a bunch of applications beyond that. As I showed you, comparing multi-stage classifiers, I was able to reuse some of this work in entity resolution work that we did with clients. Some of it's contributed to the Practical Data Privacy book from my colleague Catherine Jarmull. And we've also been able to use it in tools for designing EV charger networks as well. So it's been great to see all these different applications coming out of the work. And with a quantitative representation like this, we can, as well as asking qualitative questions, we can start to ask quantitative questions as well. And so looking at the graph, the libraries that are most represented there, matplotlib and numpy, as you might expect. Also NetworkX, I can highly recommend, and OR tools have come up useful for a number of projects. If I think back to that early part of my maths-intensive career, a library was a building that you went to in the hope of finding a textbook that might have an algorithm in pseudocode or C that you would then have to translate into your application and exhaustively test for weeks before being able to release it into a production solution. By comparison, Python library today is incredibly easy to get started. So instead of a months or weeks cycle time, we're up and running in minutes. The documentation is generally very good and supported by lots of examples. And of course, you can always go and play if you have an interesting problem to learn more about them as well. And in general, I find them very, very mathematically expressive. So actually guide you to the form of the solution that you need as well. And Python as a language is quite nice in that respect as well. Things in code look like they would in maths as well. So the overall lessons from today, and thank you for indulging me, to be driven by interest, to be opportunistic with energy. Small steps in problem and solution complexity are pretty important to be able to take those small steps to deliver outputs. I've seen the learning cascade through that process and the real-world applications becoming apparent, especially as you then know where to look for them after doing projects like this. And I hope you're able to take away that you can find inspiration anywhere that you're curious, that with a structured process, even for a nebulous question or a vague starting point, you can make progress in demonstrable small steps. That there's a lot of resources out there in the Python ecosystem. Those libraries that I shared from the Maths Whimsy repo are only a small subset of what I've used across all those projects, and that those returns accumulate. So the more you spend time in the ecosystem, the more you learn what it's possible of achieving. I'd summarise it maybe as, if you look at simulation as a technique that we might use, it's a great technique for learning whenever it's hard or costly to access the real world. And these Maths Whimsies are simulations of real-world problems that circumvent the hard or costly bit, and so help to accelerate my learning. And with a similar approach, you might accelerate your learning. So that's it from me today. You can find the examples at the Maths Whimsy repo and the write-ups at my blog there if you would like to.
Thanks, Dave. I'm afraid we probably have time for one question. There we go. There's one over there. Yes.
You appear to be presenting this as kind of the way you have learnt new technologies, explored ideas and whatnot. I wonder if you had any thoughts about this as an approach or as a technique, either in a formal education setting or in an in-house, staff development kind of capacity, using similar techniques in that kind of space.
Yeah, I think it's applicable in both very much. Open-ended project-based learning, really helpful in formal settings, and it is advice I give to people I work with and within our team and at client side as well, if they're looking at picking up new technologies, as well as formal learning materials or theoretical learning pathways, to pick projects that they're interested in because those often uncover things that aren't covered in the formal learning pathway, and clean data sets that might be provided with typical tutorials. Maybe there might be a parallel that we might draw with the performance of, say, ChatGPT and Copilot for reproducing code examples. They're good at doing the things for which there's a lot of support, a lot of resource out there. But if you want to solve new problems and atypical problems, you've actually got to get your hands dirty with the outside of toy. Well, I mean, these are toy examples, but they're new and they're different. They're not as curated as you might find in a tutorial.
Thank you.
Yeah.
Thanks, everyone. We've got a couple of moments of changeover before the next talk.